Hello, folks. Welcome to Science Talk. I am the host and resident oceanographer and climatologist, Jim Massa. I'm going to do a short little presentation here, taking you through a bunch of updates, if you will. In this first graphic, we're looking at the median sea ice extent on the day of the Arctic minimum. Okay. In other words, this would be typically in September, the oceanic summertime. And you have the most melting, most of the ice is melted away. So on the left side graph, we've got 79 to 89, 10-year average there. And this is, of course, from the Alaska Center for Climate Assessment and Policy. So Rick Toman provided these graphics. And what we're seeing here is, if you see the blue areas, ice concentration is less than 15%, meaning at most 0 to 1 year sea ice that has not survived a summertime. It could also be open waters. The white is ice concentration 15% or more. This is where we start getting into the 2, 3, 4, 5, maybe 6 year sea ice. A 3-year ice is one that has survived several summertimes. So we see that here on the left side. Look at the right side. September 13, 2020. Look at this. It's really what's hanging out in the, off Greenland, the Canadian archipelago. Chukchi is ice-free. The Beaufort, you got this little intrusion here. That's a function of a surface current. The reason this is where the Mackenzie River Delta is about here. So you got that influence there that's preventing that from freezing. But look going on here on the Eurasian side. Okay, you got the Barents, the Kara, the Laptev, the East Siberian Seas, totally ice-free. Amazing. Absolutely amazing. And when you look at the latitude, this is 60, that's 70, this is 80. And you look over here on the Eurasian side, basically 85 degrees in south is not going to be any sea ice. So as a comparison to median sea ice extent on the day of the Arctic minimum sea ice extent 79 to 89, and the preliminary day of the minimum extent this year, dated as we see here, September 13, 2020. As climatologist 49 says, and that's Brian Brettschneider, it's as if something has changed. A little sarcastic tone there. But yeah, this is what warming is doing, folks. This will change productivity. This will change how heat is absorbed and distributed. Instead of being reflected back to space, it's now absorbed. A major contributor as to why the Arctic is warming so much faster. So now let's look at this reconstructed Arctic sea ice. Okay, so this is a reconstruction of late summer Arctic sea ice extent over approximately the last 1,500 years or so. Figures reproduced from nature.com, articles Nature, there's the URL for that. The overview is climate.gov/news-features. 2017 Arctic Report Card, sea ice melting unprecedented, at least 1,500 years. And you can go to sites.uci.edu, Zach Labe, no Z Labe, but that's Z's for Zach, Arctic sea ice figures. And that's a very, very useful website there. So let's take a look at this. Now, it goes back to basically 500 to the present, to 2000. So we're looking at the extent, and if you look at this, the units are in 10 to the 6, so that's going to be 1 million, and this is square kilometers. So this is surface area. The light blue line that we see here, okay, that is basically the average. Okay, it is based on Kennard et al. 2011, found in Nature. That's what this one referenced, that URL. Then we have some direct observations starting, in the late 1800s or so, and that's the red dashed line that you see here. Okay, and what is this blue? That's the 95% confidence interval. So we often do this in stats. We put a 95, 99% confidence interval around the mean, and the confidence interval includes include what we call the standard error, which is basically the error that is assigned to the situation at hand, because when you take measurements, there's going to be randomness in the system. There's going to be error. And you'll note that as we get closer and closer to the present day, the error decreasing. That's because our techniques, our measurement ability to measure is improving, as is the technology. So what does this 95% error mean? Okay. Now, when we put a confidence interval, I said we use the standard error. To calculate the standard error requires use of the standard deviation. Standard error and standard deviation are two different measures in statistics. Okay. I've done some videos way back in the past about intro to stats. You can look at those. If you want me to do an updated version of stats, looking at confidence intervals and so on, measures of spread, etc., and other aspects. They even did one linear regression. Drop me a comment, if you'd like to see such a presentation, and I can put one together. So, what is the 95%? Well, let's back up a little bit. Oftentimes, you'll see in a paper they'll present something, and they'll say, "Here are the measurements." And then you'll see in the, be like a table, and it'll be X bar plus or minus SD. X bar, and X with a horizontal line on the top of it, is your mean. That is your, what we sometimes think of as the average. Add up all the numbers, divide by the number of entries, that's your average, that's your mean. Well, we can then calculate the standard deviation based on how far the individual measures were in relation to the mean. In other words, standard deviation is a measure of spread. I could have, two distributions. Let's say I have 50 plus or minus 2.3, 50 plus or minus 11.9. The 11.9 tells me I have a greater spread of the measurements. The 2.3 says I have a very tight clustering of the values. And with that, you're going to find out that when you have a small standard deviation, your confidence interval will be smaller. So what is the confidence interval? The confidence interval basically tells you the range that the true value will be found in. So if I calculate a mean of 50, whatever it might be, and I calculate a confidence interval around it, and the result of the confidence interval is 42 to 58. That means whatever it is I am measuring, the true mean will be found in that interval from 42 to 58. So now you can see that the larger the standard deviation is, the bigger will be this interval, the bigger spread. So we have to make a larger confidence interval to accommodate the increase in error. Conversely, you decrease the standard deviation, the confidence interval will shrink, because that means we have a really good handle where the actual value can be found. So as we look here, if I look at, say, the year, say 750, that looks like it's about, say 9.4 times 10 to the 6 square kilometers. And the confidence interval will be anywhere from, say, 8.2 to about, say, 10.3 or so. In other words, the true value would be in that interval. This is the mean. This is the confidence interval, which includes the standard deviation. And as you can see, it isn't until we start getting into about the 1750s that they start tightening up, even perhaps a little sooner. And then when we get into the late 1900s to present day, well, there's very little error because we're using satellites. So we know what the hell is going on. So then the question is, how did we reconstruct this in the first place? Isotopic fractionation. Because we can then take the sediment cores and look at the organisms. And by looking, you take sediment cores, you do a transect, you take sediment cores, you look at the isotopic fractionation in the organisms, and is the O18 to O16 higher or lower? If it is higher, that means there was more ice. If it was lower, that means there was less ice. And we can then get an idea, it must have been sea ice to here, or there was no sea ice to this location. And you do this across the basin. So it's a lot of hard work, a lot of sampling, a lot of analyses. But notice what's going on here. Yeah, you've got some oscillation. Some of this might be related to Milankovitch cycles and just seasonality. And then look what happens getting into the late 1900s. Flunk, it just nosedives. It nosedives so that the observation here in a little past the year 2000 is less than that low value for that confidence interval. This shows you how drastically sea ice has been disappearing. And now let's look at some surface temperature relative to the 51 to 80 mean. That's a 30-year time interval. So we look at on the left-hand panel, August 2020. Then we look at June, July, August 2020. And then we look at the last year, September 2019 to August 2020. So global surface air temperature anomalies over the last month. That's this panel. 3 months in the center, 12 months on the right. Parts of Siberia have observed temperatures more than 5 degrees C above average over the last year! Exclamation point. Map was created by Columbia.edu. Yes, it is the URL to take a look at that. So let's look at this August 2020. Okay, look at the chart here. White means there's no deviation from this 30-year average. Getting to the blues and purple, it's cooler than the 30-year average. Get into the pale yellow, into, I guess, brown and really dark reddish brown, whatever that is. And you see that it's getting much, much warmer. So what are some of the interesting things here we see here? Most of the northern hemisphere is warmer than average. Look at what's going on with most of Europe into the UK. Look at what's happening in Western Siberia. Central. I want to say Central Siberia. Yeah, Western Central Siberia. Eastern Siberia did cool down a little bit, as we see over here. That wasn't always the case. It did cool down a little bit. That was a function of the Arctic dipole and the Arctic oscillation doing a little changing around a bit. It was very, very warm. We see some coolness right here. This, by the way, and you'll see that is persistently cooler. Why is that? This is where you have some deep water formation coming off the continent of Antarctica. That's very cold water. It's going to sink, but because it's so cold, it's going to make the air above the waters and the nearby land cooler than usual. A lot of white in the eastern equatorial Pacific, which means it was average. But even when looking at the southern hemisphere, there's a lot of places. We do have this hot spot on the in Antarctica. Couples hot spots here. Very interesting. Nope. I wanted to. Not ready for that one. Don't know why I jumped to that. But anyway, so we see some very hot spots here. Now, what's interesting here? See this white spot here? That's average temperature. Here's Greenland. Usually, this will be cooler than average because you've got all this meltwater here. That's cold water. That's being, from the melting of the Greenland ice sheet, that cold water is keeping the temperatures cooler than usual. It's also preventing sinking. So that's just August 2020. Let's look at the 3-month, June, July, August. And we see pretty much the same story. Maybe now we have a little hotter spot here in Antarctica, but we pretty much have the same story. We don't have the cool spot in eastern Siberia. This spot that was kind of about average was warmer. You can see right there, corresponds to that. So, looking at the chart, that's about, 0.6 to 1 degree C above average. And then look at the last year. Look at the Arctic Ocean. Look at Eurasia. This cooking. And we even have this. This is that hot spot there where that was a Verkhoyansk, that town that recorded 100.4 degrees Fahrenheit, a record. You can just see how hot it was. In fact, when you look at the last year, most of the planet was warmer than usual. A couple places where it was average, very few places where it was cooler. This is showing us that things have really been warming up. Now let's look at global sea surface temperature departure from the 20th century average. In other words, we're going from January 1900 to September 2020. That's 121 years, right? Include the endpoints. 121 years. So the horizontal line is your average. So blue means it was cooler than the average. Red, it was warmer than the average. So this is your departure. You notice the scale only goes down to minus 0.6, where it goes up to 1 degree on the warmer side. So the scale is not symmetrical. But you'll notice that up to about 1940, with a couple of almost, blips, it was cooler than the average. We got some coolness in the 50s, basically interrupted by 52, 53 in here. But the first half of the 50s was cooler. Then we had some warming in the 60s, a little cooling spell there, about 65 or so. And then, so we get these ups and downs, which is kind of reflecting of ENSO influences. And then look what happened starting in the late 1970s. Wham! And you'll see how the departure is getting higher and higher, warmer and warmer. This is the ocean. Remember, high specific heat capacity. 532 consecutive months. Okay. That's like 44 and a half years. Oh, yeah. 76 to 2020. Yeah, it's 44 years. Right? 532 consecutive months. It's been hotter than the average. The September global average sea surface temperature was above the 20th century average for the 532nd consecutive month. Now, here's another thing I want to discuss with you. There's some graphs that have been constructed showing how regions of the U.S., and these graphs were constructed by NOAA, so you can always go to the NOAA website to look for them. How the regions of the U.S. and other places in the world have responded to the warming planet. Many of these graphs not only document the fact that average temperature is warming, either in a year-by-year comparison or current temperatures compared to, say, a 30-year average from 81 to 2010, or as we just saw, 51 to 80, that 30-year average. Some others will look at 50 years from 71 to 2020. You get the idea. A whole bunch of comparisons. They also do a month-by-month breakdown. So not only are we documenting that, yes, things are warmer and warmer, we can now look at month to month, what is the month that has warmed the most for a particular region. What we're finding is that in a lot of areas, overall, it is much warmer. In a lot of these areas, every month is much warmer, but there's usually a month where it is most warmest, right? It has warmed the most. That's what I want to say. So, in the U.S., for example, the Pacific Northwest region, there's been overall warming, but the month that has warmed the most on average is July. Makes perfect sense, given that it is not much later after summer solstice, where heat energy input is greatest, allow for specific heat to do its thing. The ground absorbs the heat, radiates it back out. The air is warmer. Makes perfect sense. In Alaska, the warming is quite pronounced because last time I checked, at least in recent times, Alaska is in the Arctic. And the Arctic, we know, is warming the fastest of any region on the planet. The warming in Alaska is well above averages of the past 30, 50, 100 years. The month with the greatest average warming is, drumroll, October. Now, this may come as a surprise, but it really doesn't. Why? Because of what's happening to the sea ice. With the sea ice rapidly vanishing, reaching new minimum extents, loss of multi-year ice, melting early in the year, freezing later in the year, there's more and more open water that now absorbs sun energy, where if you had ice, that energy is reflected back into space, keeping things cool. This energy has been absorbed by the water, is now given off as the ocean cools down on its way to freezing. And remember, for seawater, because of the salinity, because of the solutes added, and the concept of freezing point depression, it has to cool below 0 C in order to freeze. That means more heat is further given off. The energy that's given off using the form of latent heat energy warms the atmosphere. This is a major reason why October is the month in Alaska that has warmed the most. It is also why instead of snow, we're getting freezing rain. It should be freezing rain, should not be a comma there. And, instead of getting snow, freezing rain, sleet is occurring in higher frequencies during October and November, which makes driving an absolute nightmare. Treacherous conditions. And there's other factors to take into account, such as the jet stream, ENSO, PDO, IPO, NAO, AO, AD, etc. So that's what's going on with that. So, let's go back to here. Right? Here's the Chukchi. Right there's the Chukchi. It's absorbed all that heat energy. It has to give off all that heat energy before it can freeze. Well, here's it's right there next to Alaska. And when you look at the breakdown of Alaska, the North Slope, as we call this, the North Slope, is the warmest, has warmed the warmest, followed by going from the Canadian border this way across the middle band into interior Alaska, and then, further south has warmed the least. because of the extent that the latent heat energy can reach. But yeah, there it is. So I wanted to show you these slides here, kind of an update, addendum to some of my recent presentations. But things are happening. And as Brian would say, it's as if something has changed. Yeah, think. So thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.